Welcome to this video where I'm going to show you a solution to the past paper for the CSEC Physics May 2018. This is the paper 2. Let's get right into it. In an experiment to determine the focal length of a convex lens, a group of 5th form students set up the apparatus shown in figure 1. The students measured object distances u and corresponding image distances v and recorded information in table 1. So, first thing you're asked to do is to complete table 1 to show values for 1 over u and 1 over v. And you're also to include units and calculate to 3 significant figures. Then, after that, on the grid provided on page 5 in the booklet that you will be provided, you're to plot a graph of 1 over u against 1 over v for 7 marks. If u, the object distance, is measured in centimeters, then 1 over u would be measured in 1 over centimeters. You could also alternatively have written that as centimeters to the negative 1 power. Then, if we're to find 1 over u values, that simply means we're to take 1 and divide it by the u values, or in other words, find the reciprocals. So the reciprocal of 20.0 will be 0.05. But notice that specifically the instruction says to give it to 3 significant figures. So that would be 0.050. Similarly, 1 over 55.6 will give you 0.018. And filling in the rest, you would get 0.033 and 0.025 and so on and so forth. So, you're to then plot those values and your graph would look like this. The breakdown of the 7 points is as follows. You'll get 1 point for choosing a suitable scale. Please make sure that you state your scale. As you can see here at the top, I have that it's 1 centimeter to every 0.01 per centimeter, right? Or centimeter to the negative 1 power. Same thing goes for the vertical scale. You also get a point for labeling your axes and having the units with them. So on the horizontal axis, it's 1 over v, and the unit is centimeter to the negative 1 power. You get a point for having a title. So here we see a graph showing 1 over u versus 1 over v. You get 3 points for labeling. You get 3 points for plotting the points accurately. And you get 1 point for drawing a suitable line of best fit. So that is where your 7 marks is allocated. Please note though that whenever you do this, you should not use just a big blob as you see there. I did this on the internet and I could not find the proper tool to put a dot with a circle around it or an X, but that is what you should use, a dot with a circle around it or an X. So this is what your graph should look like. And later on in the problem, you're asked to find a couple things from this graph, namely the gradient. So that is where you see that triangle there drawn, and those 2 coordinates are taken from the line of best fit. Ideally, you should take your coordinates from the line of best fit from 2 points that are not points that were plotted. So you'll see there 0.010 as our x coordinate and 0.056 as our y coordinate. And the other pair of x and y coordinates, 0.060 with 0.006. So if we're to calculate the gradient of the graph, first thing we should do is to write down those coordinates. And so we'll use the formula that the gradient is equal to the vertical rise over the horizontal run, or y2 minus y1 over x2 minus x1. So substituting into our formula, we'll have 0.006 minus 0.056 divided by 0.060 minus 0.010. So that will be a negative 0.050 centimeters to the negative 1 power divided by a positive 0.050 centimeters to the negative 1 power. Here, the units of centimeters to the negative 1 are going to cancel out, and the negative 0.50 divided by the same thing but positive will give you a gradient equal to negative 1. For this graph, there are no units because they cancel out, right? But in general, please make sure that you have the correct units for your graph. You may notice that here, this graph question to calculate the gradient is only for 4 marks. Typically, it is for 5 marks because you are to include the gradient. Here, since no gradient is there for the answer, it's only for 4 marks. Next, you have to state the value of the intercept c on the 1 over u axis. So here, if you extend your line of best fit to reach the y-axis, you would see that it would reach at about 0.061234, 0.064. Alright? 4 little marks up there, but again, remember, depending on the scale, it's going to be in jumps of 2 here, so 0.068 centimeters to the negative 1 power. Therefore, to calculate the focal length f, we're to use this formula that is given, and we first need to rearrange it to make f equals 1 over c. So when we substitute 1 divided by 0.068 centimeters to the negative 1 power, will give us that the focal length is approximately 14.7 centimeters. Here, the 4 marks are given for rearranging the formula, for substituting into the formula, to calculate the correct answer, and to have the correct units with the answer. Alright, so here the unit for the focal length is centimeters because that's the reciprocal of the reciprocal. Lastly, for question 1, we're to complete figure 2 to show the paths of rays 1, 2, and 3 as they pass through the convex lens represented by the dotted line. Recall that a convex lens is also a converging lens. Alright, so the paths of rays 1, 2, and 3. That very first one that passes right through the optical center is the easiest one to draw because any light ray that passes through the optical center is undeviated, or in other words, it goes through as a straight line. Then ray 3 would be the next one that I would draw because any ray that passes through the principal focus, capital F, when it reaches the lens, it will refract in such a way that it goes parallel to the principal axis. Then ray 1, the kind of tricky ray to draw. Technically, if a ray was coming in parallel to the principal axis, then it would refract in such a way such that it would pass through the principal focus, capital F. But notice that ray 1 is not coming in parallel to the principal axis. It's actually coming at an angle. And then also remember that this is a convex lens, which means that it is a converging lens, so it wants to bring the rays closer together as much as possible, or in other words, it will deflect it more so towards the normal. So this ray won't go straight and pass through F, but it will go down because it is refracted more. So those are for the 25 marks. Question 2. Part A, Part 1. An atom consists of 3 types of particles: protons, neutrons, and electrons. We're to complete the following table to show the charge of each particle. So this is a rather easy start to this question. The charge on a particle that is a proton is positive. The charge on a neutron, you could say, is neutral, or you could say there is none. And the charge on an electron is negative. So that's for 3 easy marks. Next, Part 2. For the element that is radium 88-226 that we see there, we're to determine the number of each of the 3 particles referred to in Part A, Part 1. So the number of protons, well, if we look at it, we see that Ra, which is radium, and we see the numbers 88 and we see the numbers 226. The 88 is the proton number, so that's simply 88, how many protons there are. The 226, that is known as the nucleon number, which is how many protons and neutrons are in the atom. So if we were to subtract the number of protons, which is 88, from the total number of protons and neutrons, which is 226, we would be left with how many neutrons there are, which is 138. Next, assuming that this is a neutral atom, then the number of electrons would be the same as the number of protons, so that would also be 88. So 1 point to state the protons, 1 point to state the electrons, 2 points to calculate the number of neutrons. Part 3, state 1 similarity and 1 difference between the isotopes of an element. So a similarity you could state is that isotopes have the same number of protons. A difference you could state is that isotopes have different number of neutrons. Part B, Part 1, define the term half-life of a radioactive substance. So you could say that half-life is the amount of time that it takes for the radioactivity of a radioactive substance to reduce to half of its previous value. Or you could say it is the amount of time it takes for half of a radioactive substance to randomly decay. So Using that second definition, we're going to solve this part here where it says the element thorium, Th, has a half-life of 24 days and undergoes beta decay. We're to calculate the time it would take for 10 grams of thorium to decay to 1.25 grams. So, in one half-life of thorium, it's going to decay from 10 grams down to 5 grams. And that calculation is simply 10 divided by 2, which gives us 5. And then it's going to keep on decaying, and in another half-life, it's going to go from 5 grams down to 2.5 grams, which is again 5 divided by 2. And if we divide by 2 one more time, 2.5 divided by 2 gives us 1.25. So after 3 half-lives, thorium will go from 10 grams down to 1.25 grams. So the total time taken would be the value of the half-life, which is 24 days, multiplied by the number of half-lives, which is 3. So 24 days times 3 gives us a value of 72 days. And that is for 4 marks, and a total of 15 marks altogether. Question 3, we're to define the term electric field. And that's easy. An electric field is the region of space where the force of an electric charge can be experienced. And that's for 3 marks. In my opinion, a very easy 3 marks if you are prepared, if you have studied. B, we're to draw the electric field formed between the parallel plates shown in figure 3. So they are 2 parallel plates, so our field will be uniform, meaning that our arrows will go directly in between the positive and the negative charges that are right next to each other on the same level. The next point is to show the direction of the electric field. So you need to know or remember, in other words, that the direction of the electric field goes from positive to negative. So when you draw this electric field, all of your arrows should go from the positive towards the negative. 3 part C, a lightning strike is an example of an electrostatic hazard, or to state one other hazard of static charge. So a possible answer you could have is that one other hazard of static charge is that it can damage sensitive electronic equipment such as computer chips. And if you're to state one useful application of static charge, you could say that one useful application of static charge is that it is used in photocopiers. Part D of question 3 says the graph in figure 4 shows the alternating voltage output from a generator. We're to use this graph in figure 4 to determine the value of the peak-to-peak voltage. So to calculate the peak-to-peak voltage, we could subtract the lower value, which is negative 10, from the upper value, which is positive 10, and that will give us 20 volts. Or you could simply have the peak voltage multiplied times 2, and that would also give you 20 volts. Then we're to determine the period of the alternating voltage in seconds. So remember that the period is the time taken for one complete oscillation. So if we look at our graph, it starts at 0, goes up to the top of 10 in a time of 2 seconds, back to 0 when it's 4 milliseconds, not seconds, let me correct myself, down to negative 10 at 6, and back to 0 at 8 milliseconds. So the period is 8 milliseconds. That's the time it takes to go to complete one complete oscillation. You could have also found that value by looking at the peaks. The first peak is at 2 milliseconds. The very next peak is at 10 milliseconds. So 10 take away 2 also gives you 8 milliseconds. Next, we're to determine the frequency of the alternating voltage from the supply. So recall that frequency is 1 over period. Oh, and I just remembered my mistake. It's supposed to be in seconds. So we need to convert from milliseconds to seconds. We do so by dividing by 1,000. Then the frequency is 1 over the period, F equals 1 over t. So it's going to be 1 over 0.008 seconds, which will give you 125 hertz. Or alternatively, you could have seconds to the negative 1 power as the units. So 1 point for the formula, 1 point for the substitution, 1 point for the answer, 1 point for the units. That's 4 marks. Question 4, we're to define each of the following terms. So specific heat capacity and heat capacity. So for 3 marks, Specific heat capacity is the amount of heat energy required to change the temperature of 1 kilogram of a substance or object by 1 Kelvin. For 2 marks, heat capacity is the amount of heat energy required to change the temperature of a substance or object by 1 Kelvin. So specific heat capacity is for every kilogram, meanwhile heat capacity is just for the entire object altogether. And next, we're to write the formula to show the relationship between the specific heat capacity, small c, and the heat capacity, big C, of a body. This is a question that has come up multiple times on multiple exam papers. It is simply big C is equals to m times the little c. Heat capacity is equal to mass times specific heat capacity. Then, using the data on page 14, which you see to the right of the screen, you're to calculate the specific heat capacity of the metal, stating any assumptions made. So, looking at that apparatus and reading the question, we are told that some students were asked to carry out an experiment to determine the specific heat capacity of a metal. They used the apparatus shown in figure 5. So there's a thermometer, there's a low voltage supply, there's a metal block, insulation, and heater. So we're told that the switch was closed for a time interval of 900 seconds and the following readings were obtained. The mass of the metal block was 5 kilograms. The change in temperature was 50 degrees Celsius. The ammeter reading was 8.5 amperes and the voltmeter reading was 12 volts. So for 9 marks, we're to calculate the specific heat capacity of the metal. So, first thing we need to do is to determine how much energy was used. And in order to do that, we have to first calculate what is the power of the low voltage supply. So power is equal to current times voltage, or P equals IV. The current was stated as 8.5 amperes and the voltage is 12 volts. So 8.5 amperes multiplied by 12 volts gives us that the power was 102 watts. Next, the energy is equal to power multiplied by time. So we calculated that the power is 102 watts, and the question states that the time taken was 900 seconds. So that gives us an energy of 91,800 joules. Now when it comes to specific heat capacity, we use our formula C is equals to heat energy divided by mass times the change in temperature. So the energy calculated is 91,800 joules. The mass is stated as 5 kilograms and the change in temperature is stated as 50 degrees Celsius. Performing this calculation with our calculators, we get that the specific heat capacity of the metal is 367 joules per kilogram degrees Celsius. What assumption did we make in this problem? Well, an assumption was made that no heat was lost to the surroundings. Our next question, question 5, A part 1, state Hooke's law for 3 marks. Hooke's law states that the extension of a spring is directly proportional to the force applied to it, given that the elastic limit is not exceeded. This is, again, another easy 3 marks. Anytime they ask for a definition or a law, it's usually for 3 marks, and if you have studied, if you are prepared, those should be easy 3 points. Next, with the aid of a labeled sketched graph, explain what is meant by elastic limit. So this is what the graph of Hooke's law typically looks like. You have a straight line originating from the origin, and that shows proportionality. And up to a certain point, it then doesn't have that characteristic anymore and starts to curve and taper off. That point is where the elastic limit should be labeled. And the elastic limit of a spring is the point whereby the spring will become permanently deformed and it will not go back to its original length. Right? And the graph curving like that and no longer being a straight line shows that the extension is no longer proportional to the force applied. In other words, any tiny little amount of force will produce a great extension. Then, part B, we're told that a steel spring has a spring constant of 2 times 10 to the second newtons per meter. We're to calculate the weight of an object which, when attached to the unloaded spring, produces an extension of 50 millimeters. And we're told that the elastic limit is not exceeded. And we're also given the formula that spring constant is equal to force over extension. So let's see. First thing we need to do is notice that the spring constant is given in units of newtons per meter, and the extension is given in millimeters. So we need to convert that millimeters to meters by dividing by 1,000. And so that will give you 5 times 10 to the negative 4 meters. Then we need to rearrange our formula to make force the subject. So force will be spring constant multiplied by the extension. Substituting our values, the meters and the per meters are going to cancel out, and we're going to be left with units of newtons. So when you multiply 2 times 10 to the second and 5 times 10 to the negative 4 using your calculator, that will give you 10 newtons. And that's the answer. Part C, we're told that the object attached to the spring in B fell from rest and hit the ground after 2 seconds. We're to calculate the velocity of the object on hitting the ground. So we want to calculate the final velocity, which is v. We're told that it fell from rest, so the initial velocity u is 0 meters per second. We're given to use the value of g equals 10 meters per second squared, so that's the acceleration due to gravity, and the time interval is 2 seconds. So we have v that we want to find, and we know u, a, and t. So the equation of motion we should use is v equals u plus at. Substituting our values, we'll have v is equal to 0 plus 10 times 2. So here, the second squared and the second, one of them will cancel and we'll be left with meters per second. And 10 times 2 is 20, plus 0, of course, is just 20 still. So that's the answer. The final velocity v is 20 meters per second. Question 6, the final question. We're given this diagram and we're told that the transformer is a commonplace technological tool used in our daily lives. Figure 6 shows one type of transformer used in electricity distribution. Part 1, we're to state the name of the parts labeled A, B, C, and D in that figure. So, part A is pointing to the primary coil. B is pointing to the core. C, that's the alternating current input voltage, and D, that's the secondary coil. Now notice that the primary coil and the secondary coil are not the same amount. In fact, we have much more on the secondary coil, and that is important to notice because the next question says to identify the type of transformer shown in figure 6. So as we see here, since there are more turns on this secondary coil, then that means this is a step-up transformer. Then part 3, we're to state the formula that relates voltage V to number of turns N in a transformer. So again, that's straight recall for 1 point. Primary voltage divided by secondary voltage is equal to primary turns divided by secondary turns. Part B, a transformer has 5,000 turns in its secondary coil and 50 turns in its primary coil. The voltage supplied to its primary coil is 12.0 volts AC, and a current of 6.0 amperes flows in its primary coil. Using those pieces of information, we're to calculate the input power of the transformer. So, power is equal to current multiplied by voltage, P equals IV. The input current is 6.0 amperes. The primary voltage is 12.0 volts. Multiplying those, we get 72.0 watts. Next, we're to calculate the voltage across the secondary coil. So here is where we'll use the formula, primary voltage over secondary voltage equals primary turns over secondary turns. And using the information I was given, we know primary turns is 50, secondary turns is 5,000. We were given the primary voltage is 12.0 volts. So the secondary voltage, V sub S, we will calculate by multiplying 12.0 times 5,000 and dividing it by 50. So the secondary voltage is 1,200 volts. Part 3, the maximum secondary current if the transformer is 100% efficient. So we know the secondary power is 72.0 watts. We can rearrange the formula to have that the current is power divided by voltage. So 72.0 watts divided by the secondary voltage of 1200 volts will give us that the secondary current is 0.06 amperes. Alternatively, we could have also used the formula secondary current over primary current is equal to primary turns over secondary turns. Notice that when it's current, It's flipped. Secondary goes with primary and primary goes with secondary. Substituting, the secondary current over 6.0 amperes will be 50 divided by 5,000. So the secondary current will be 6.0 amperes times 50 divided by 5,000, which will give us the same 0.06 amperes. Good luck on your exams.